Last time in phase equilibria, we covered departure functions. What I want you to know about departure functions is that they measure deviation from ideal behavior. So if you have a problem and you have a real fluid, you cannot use in general the heat capacity. So we saw that when we did the departure function for enthalpy from ideal behavior. And I didn't spend a lot of time on departure functions. It can get pretty repetitive and get pretty involved with the derivations. So we did enthalpy. So we did H minus H star. You should be aware of, and you should definitely read in your book in section 6.4. Section 6.4 has more info, and there are other departure functions, has more departure functions, especially for properties like enthalpy. I think internal energy is in there as well. And they also show you for various equations of state too. So we only did the departure function for enthalpy for van der Waals, but you can also do for Pang-Robinson, for Suave-Redlich-Kwong, any other equation of state. Next week's homework, I think I'll probably have you derive what the departure function for entropy will be, and then again, section 6.4 will have some useful help for you there. So today what I want to do is get into equations of state. Been alluding to the various equations of state. We'll talk more about them today. Equations of state. And again, the ideal gas law is the simplest and easiest to solve. Ideal gas law is, I'm going to write it in a form that the other equations of state typically are written in, that is solved for P. So P is equal to RT over molar volume. So I want to try to imagine the observations that would lead to the derivation of the ideal gas law. Let's say we have our classic gas in a piston cylinder device, and we are going to keep the temperature constant in this experiment. So we've got some gas inside here, and we are going to measure the effect of pressure on changing volume. So we can squeeze this piston down. So let's say we squeeze it a little bit, and we've got a pressure sensor that will measure the pressure inside. So at the start, we may say that we have a certain molar volume. We can measure the molar volume because we know the volume of a cylinder, and we would measure the pressure inside with that pressure sensor. So this is taking data. And as we squeeze on this piston, we may see that as we decrease the volume, the pressure starts to increase. And roughly, we may see that it's a linear relationship, and it's an inverse relationship. Sorry, not linear. So it would follow the shape of a graph for 1 minus x. So it would look like this for an ideal relationship. So you can continue taking data points, and we may see that the ideal gas law fits quite well so long as pressure is under a certain amount. So if we keep doing this, we may see some deviations from ideal gas behavior. So another flaw that we may see, that at some point, instead of continuing to increase pressure with that same trend, at some point, if we keep compressing this gas, it is going to do what looks like a jump over. And from that point on, the pressure is going to be very sensitive to small changes in volume. So what happens here in an ideal, or in a regular equation of state, is that this refers to the liquid states, and this refers to vapor states. So the ideal gas law does not account at all for this jump over to liquid. So ideal gas law is not good for liquids, obviously, because if I curve fit, which is mostly what this section is, right? This fit of my vapor data points doesn't account for this liquid at all. There's another fundamental flaw of the ideal gas equation of state, which is fundamentally we could have volume that is going to zero. And at a certain point, volume can't go to zero because the molecules themselves take up space. So I cannot keep compressing the molecules such that they occupy the same space. And that was the impetus behind the first cubic equation of state, which was van der Waals. So the van der Waals equation of state accounts for the fact that volume can't go to 0, and van der Waals says P is equal to RT over V minus B minus A over B squared. All right, in the van der Waals equation of state, the parameter B refers to the minimum volume that the molecules occupy. And you can also think of the two terms as the repulsive and attractive forces. So van der Waals calls this the repulsive term, repulsive pressure. And the second term is the attractive pressure. So you can think of an analogy with humans in a room. This is, of course, before the coronavirus outbreak. But if you wanted to measure like what the optimal space you would want to be spaced in a room is, imagine like you're in like an arena or something with only 3 other people. You wouldn't want to be spaced that far apart, because if you wanted to interact with each other, you wouldn't want to scream, and you'd want to be kind of in the same general vicinity as each other. So you may think like the lowest energy state, you're going to want to go closer to those people. Maybe 6 feet away would be the lowest energy state. So that's where the attractive term comes in. So molecules are going to want to associate with people at a certain level. But too close, and then you start getting into each other's personal space, and at that point you maybe want to back away. So any cubic equation of state takes into account the balance between these attractive and repulsive forces. Another benefit to the cubic equation of state is that you can accurately model both the liquid and vapor portions of this curve. So one potential curve fit would be to literally just trace exactly how the data goes. But this is unrealistic and also not differentiable because you have cusps in this function. It also looked like it'd be piecewise, right? So it wouldn't be very wieldy to use. So instead of that, what the cubic equation of state does is it fits a part down here, and then it has to be negative necessarily, and it comes back up here, and then comes down like this. So this is the general form of the cubic equation of state, and the only downside here is that you have an entire region of the curve that doesn't make any physical sense. So it breaks down at a certain point. So anything in this area that I'm dashing is not making physical sense. So these are not physically possible pressures for volumes. So the actual behavior actually follows exactly what the data points show, but the modeled equation of state, it has to have these parts such that the function is differentiable at all places. So I didn't draw this super accurately. I'm going to try one more time. So I want it to be differentiable, but only barely. And that's a little bit better. All right, so if we wanted to solve this for a specific value of pressure, so say we wanted to know what the molar volume was if the pressure was some value. So let's say my pressure is, oh, not there. Let's say my pressure is high. Well, wherever it crosses, whatever my pressure is, wherever it crosses this equation of state is going to be my answer. Problem with the cubic equation of state is that sometimes you can have 3 potential solutions. So say my pressure is here. I have 3 intersections with this plot. So I've got an answer here, an answer there, and an answer here. So if I have 3 answers, and this stems from the fact that my equation of state is cubic in volume, which volume is correct? And because these first 2 fall in this dotted region, which is not physically relevant, right? It's just an area of the curve such that I can have a continuously differentiable function that describes both the liquid and the vapor. I know that these two aren't right. So I know that I have a stable phase that is all vapor, and my correct answer must be to the right. So sometimes you have to use logic and common sense in determining which one of your roots is correct. All right, so that's all for this video. In the next video, I'll show you how to use Excel to solve one of these equations of state.